This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Or only one input is changing at any one instant in time at the input of the gate. There were some others, but they're second-order effects. Now, we went through and we looked at logical effort in certain examples. And we defined path logical effort, path electrical effort, and path effort, and we rewrote or we determined these formulae. And importantly, what I emphasized was you have to make sure that you know this, right? So make sure that you know it. We talked about branching efforts, and then we worked out what the delay of the circuit in terms of logical effort, branching effort, and parasitic delay was. And we did an example here, which was how to actually work out what the delay that we would expect through this relatively simple, logic circuit, including something that we've mimicked as the load, where we're saying that the load that's connected here is we're emulating it or approximating it as a capacitor of 20 units. And again, I re-emphasize when I'm saying 20 units, it's 20 units of equivalent capacitance to an inverter on the minimum process. Good. We then went through and said, well, this is all good and great, and it allows us to estimate what our delay is going to be under certain circumstances. How about if we want to work out how should we design each of these components so that we have minimum delay, right? And then what we went through is, and I actually said for you guys to prove this for yourselves, was that the minimum delay through a collection of circuits occurs when you've got minimum path effort delay in each of the components. And if you go through the mathematics, you can actually prove this for yourselves. And then what we've gone through is then said, well, if we believe this, or we actually have proven this, then we can actually work out the delay for any kind of circuit, and based on what the minimum, minimum path effort is going to be, or effort for each of the components. And we can rewrite the total delay as n times the effort, where each one's got the same level of effort, the total efforts of 1 on n plus the parasitic delay. And what it actually said to us, or what it actually says to us, is that if you've got the number of stages and the total path effort and the parasitic delay, you don't need to know anything about transistors in order to work out what the minimum path delay is going to be. What it allows you to do, or this machinery allows you to do, is actually to estimate it, right? And then what we said was, hey, if we estimate it, or how do we estimate? How do we use it? And there, what we went through was, hey, if we've got the effort for unit I, the logical complexity or logical effort, times the output capacitance for the previous stage, we can also work out what the total capacity or the capacitance for that stage I is supposed to be. And we went through an example here where we determined that. Then again, we just a little bit more. I also went through the following, which was, hey, if we're trying to drive, and in this particular case, what we've got is we've got an inverter trying to drive potentially some some other gates. And you can think of this, maybe this one important example here is you're trying to drive a clock, right? So here you've got a clock. Now you can say, well, I'm inverting it, but that doesn't really matter, right? That's just changing where the edge transition occurs. And you're driving 64 registers. Which one of these would actually be the fastest? That's one of the examples, right? And it's just showing to you that by appropriately adding an appropriate number of inverters, you can actually do better than just trying to drive with, you know, with one drive stage. And essentially what we did is we calculated the total delay in terms of logical effort, path effort and parasitic delay, and we worked out that this one was the one that gave us the minimum delay. The fastest. Minimum delay, fastest. Yes. All right. And what we also did was I asked it a different way, which was, hey, let's suppose I've now got something which has got so many units of logical effort required, or path effort required. How can I work out what the optimal number of stages is going to be if we, you know, for example, if we had you know, this situation and I asked you how many stages, what you can actually do is convince yourself that it's actually 3 stages. Anyway, that's what we learnt, right? And it's super interesting and it's super useful, right? And you should spend some time, you know, doing some examples and spending a little bit of time trying to understand and make sure that you convince yourselves that you know how to do all this. Okay? Critically important. Now, the thing that we're going to talk about today is power. All right? Now, I'll give you a little bit of background, and then we'll talk a little bit, have a little bit of discussion before going into the rest of the slides. And I was, and again, I've taken this out of a textbook that I'm using, but you know, it's just daunting to start seeing the amount of power that's actually consumed in the data centers, right? You know, in 2006, and I'm sure this is probably 10 times this at the moment, it was 61 billion kilowatt hours was used in data centers around the world. Just phenomenal, right? And the reason why we're real, other than, you know, appealing to the environmentalists amongst you, the other reason why this is something that's critically important is that the other thing that power dissipation or power consumption does is limits chip speed. Right? Now, can someone tell me why they believe it would limit power consumption or power dissipation would limit chip speed? You want to have a go? Yeah.
Is it because of temperature?
Okay, and? Yes, temperature, and what's the issue? All right, so temperature, yes, I mean, power dissipation means...
I was just guessing.
No, but it's right. You're absolutely on the money. Okay, so what happens is the chip gets too hot, and it starts, if it overheats, then all of a sudden, all you know, if you had your...
The resistance will increase with temperature increase.
Resistance isn't the most important thing. It does affect it, but essentially what happens is the way that you build chips is actually you anneal them. You implant and you anneal in order to have those tubs. Remember, you have, for example, if you had an NMOS transistor. Okay. Now, if you increase, there's two issues, right? The first is as temperature increases, the performance of your transistor decreases. It usually goes as T to the minus 3 on 2. Now, then, which means that your gain and the like decreases. But also, as your colleague has just pointed out, the other thing that happens is the chip itself gets hot, and all of a sudden you've got the N wells or the P wells, whatever. They start, if it gets too hot, what actually happens is they start not being well defined any longer, and actually you get those wells are no longer wells anymore, and all of a sudden, you know, it just becomes this big mess, right? So therefore the chip itself destroys itself. Now, and that's one of the things that really limits the performance of chips, right? And that's where, you know, potentially the company that I work for has been making a big deal about it, because some of their processes, or AMD's been making a big deal about their processes that don't require as much cooling in order to get, you know, 4 or 5 gigahertz of performance, whereas, you know, the competitor, I don't know if you saw, was demonstrating a 5 gigahertz chip, but what they did, what they said, oh, look, our chip works at 5 gigahertz, but they didn't show you the liquid cooling that they were hiding at the back in order to be able to make that chip work, right? They were saying, like, our chip works there also, but the truth is, well, yeah, but if you need this massive refrigerator to be able to cool liquid in order to get your chip to run at that speed, well, it's not really practical, right? Yes, you've made it work, but, you know, imagine having to carry a fridge with you every time you carried your laptop. You know, not particularly useful. Anyway, so that's the other reason, right? So what we'll see is that power dissipation goes as a half CFD squared, and we'll talk about that in the next few slides. But essentially, power dissipation is one of the important issues that limits overall the speed of a chip. And there's a lot of things that you do in order to be able to make that chip more efficient, right? So in terms of power consumption. Now, the other thing that you might find interesting, and it always shocks me, is that the power density in one of these modern processors is actually higher than the power density in the nuclear reactor. Right? It's not the total power, but the power density. So you can imagine what we're talking about. You know, the amount of joules per micrometer squared is actually phenomenal, right? And that's one of the biggest limitations in terms of being able to make these devices run faster and faster, right? So if you were able to put a liquid nitrogen cooler on your EPIC processor, let's one of our AMD processor or the EPIC processor, and you put liquid nitrogen on it, you run it much faster. Right. Anyway, I thought that would be something interesting. You'd find that how do you call it? Interesting and exciting or whatever. Okay. So really, one of the things the reason why we're doing this and why I'm talking about power consumption in a high-speed electronics course is that the power dissipation is important, not only in terms of not requiring fans, etc. It's important because it also limits speed, and that's what I'm trying to emphasize, and that's why I'm teaching you about this. Now, a lot of the stuff that we're going to talk about next in the next few slides, like the back of your hands. You've been doing this for the last 5 years at least. I know a lot of you have done an undergraduate or bachelor's in engineering, or have got an undergraduate in engineering. So, but anyway, let's go through it anyway. So we know that power is current times voltage, and we know, and that's essentially power is joules per second. And if we integrate the joules per second, we actually get energy, which is joules. Integrate over time. Now, you've all seen a capacitor, right? And you know that the voltage across this capacitor is, is related to, or the voltage is related to the charge of through this constant called C, which is the capacitance. And something which you've probably seen, again, thousands of times before, the rate of change of charge on the capacitor is equal to the current either being fed into or taken out of the capacitor, and that's equal to, again, C dV dt. I'm making the assumption, and which is not always true, in most cases is never true, that the capacitance is constant, right? But anyway, for most first order approximations and for most of the things that we're doing, we can assume that the capacitance is constant, and the only thing that's changing is the voltage. Now, what you're able to do is, you can substitute this into here, integrate it up, and you get that the energy stored on a capacitor is a half CV squared. Right? No big deal, but that's just the energy that's stored on the capacitor. Now, is this process, so the question then is this process 100% efficient? Is it 98% efficient, 99, 95? Any guesses? How efficient do we think it's going to be? Okay, let's work it out. Okay, so let's now look at an inverter which is charging a capacitor, a load, right? And we can do this in a number of ways. This is just allowing us to do it in a particular way which is relevant to our course. I can actually have two switches here instead, right? I can have a switch charging the capacitor and a switch then which would be used to discharge a capacitor. So let's go through the calculations, and what we see is the charge, the energy is I VDD integrated over time, right? And we know that I, the current, is CV VDD, right? So V is the rate of change of voltage across the capacitor. VDD is the supply voltage, right? And when you integrate this up, what you find is that the energy that you've consumed, or the total energy that's being delivered by the power supply, is C VDD squared, right? We've worked out and said that the amount of energy stored in the capacitor is a half C VDD squared. So what does it say about the efficiency of this process? 50%. So every time you're charging a capacitor, 50% of that energy goes into generating heat. Okay. So we also go through this process. So there's energy which is dissipated as heat when we're charging the capacitor, and we know exactly what it is. But we also have energy which is dissipated when we go from a 1 to a 0 transition, right? So therefore, the amount of power that's dissipated, right, is the power on the capacitor itself. So it's a half CV all squared. Right, so therefore you've got power that's dissipated in charging, power that's dissipated when you're discharging, right? So therefore you know the total power or the total heat that's generated as part of this process. Now, if you're switching this with some particular frequency, you can actually then say, well, the power is C VDD squared times the switching frequency. Okay, great, okay. But if we want to use this for our benefit in order to do something useful, what we do realise is a lot of times not all these circuits are constantly switching, right? Correct? So which, in a device, so if you had a device, a synchronous device, what's the element that's always switching, changing? The clock, right? So therefore that has an activity factor of 1. So what we're going to do now is going to define this thing of this concept of activity factor, which is certain elements change all the time, like a clock. It changes every cycle. It goes from 0 to 1 and back to 0. But there are other circuits which don't really do anything. Maybe they don't do anything at all. They just do something very rarely. Or they might change some percentage or some amount every so clock cycle or whatever. Right? So we want to be able to work out that activity factor so that we can actually then estimate what is actually happening in this device in order to be able to have an estimate on our power consumption. Okay? So what we're going to do is we're going to define the power is equal to A, an activity factor, C VDD squared times the frequency. Right? So in the past here what we did was we had the power was CV squared times the switching frequency, but what we're saying here is let's define the switching frequency to be A times the clock frequency. Right? And if we do that, we can rewrite the power in terms of the clock frequency and an activity factor. And just in the interest of clarity, we define an activity factor as being the probability that a circuit node transitions from 0 to 1. Right? So all we're saying is the activity factor is how often, or what's the probability every cycle or every clock cycle we go from 0 to 1? Okay. And what we've said, and we've just described this, and your colleague there has just pointed out that a clock has an activity factor of 1, but not all other components or elements or gates have the same activity factor. It's almost, I can almost guarantee you that they're probably closer to half, except for, you know, clock buffers and things like that, right? Because not everything's constantly transitioning with the clock. Anyway, so what we said is data lines transition usually at an activity factor of less than a half. And what we'll do is we'll talk about how to estimate or determine activity factor in a few examples. And we'll do that in probably two or three slides' time, but I was just wanting to introduce activity factor and just make you aware of it, and then what we'll do is we'll talk about it in the next few slides. Now, what I wanted to also point out was, we've talked about power dissipation, and what I wanted to point out is there's two types of power dissipation, right? Can anyone, and here I say there's dynamic power dissipation and static dissipation, right? And I've given you some examples. Can somebody, because I feel like I'm going really quickly in this lecture, maybe I'll get someone to explain to me. Does anyone want to explain to me dynamic power dissipation? Will?
Charging of the capacitors.
Right. Right, so you're actually charging the capacitors, right? So that's part of it. Now, the other thing that also contributes to dynamic power consumption is that in CMOS circuits, we're always making the assumption that the PMOS device is actually off when the NMOS device is on, and vice versa. That's not necessarily true. Sometimes there's a little time instant where both of those components might be on, and therefore what happens is you've got what we refer to as short circuit current. Right. Now, for the most part, what we're doing is we're assuming that the power dissipation is dominated by the charging or discharging of capacitances, but this also plays a non-insignificant role. So really, if you're doing this properly and you've got large circuits and the like, you should also consider this, because this plays an important role. Now, static dissipation. Do you want to tell me about static dissipation? You can say no, and I'll... yes?
Well, so leakage is transfer.
What does that mean? Yes, I can read too. No, righto. You know what that is? Okay. Does anyone know what it is? The sub-leakage, I'm talking about the sub-threshold leakage. Okay. So remember, when we're making our assumptions, it was, I'll get this wrong, so you're going to all laugh. So it was K, squared. But there's also, I was also looking in the triad region, and I forgot the triad region.
It breaks down, so
yeah.
how to draw it?
Yeah, that's a good idea. Okay, all right. So what happens in this, okay, so usually you've got, and this is VG, okay, so, and then you've got, well, almost something like this, right? So if VGS is less than VT, you still get current going through the transistor, right? But it's small. It's not as large as when it's on, right? And this is what we're talking about. We're talking about there's leakage current, or sub-threshold, right? So this is the threshold. We're below the threshold, but technically the current isn't zero, right? And I can draw this. I guess if I did this, this might be better than just say if you're in this region. Anyway. All right. So what that says is, even though, unless the voltage is 0, well, the VGS is 0, or it might even need to be below 0 because there's 0 VT devices, there's a little bit of current still flowing. It's not as large as, when the transistor's on, but there's still current, right? And partly, I don't know if you can actually see that because can most people see that? Sort of? Yeah, all right, good. That happens, right? So, what was I saying? Anyway, I was saying that the transistors, the gate of a transistor it's got a threshold. What's actually happening is it's not 0 or even below 0, so therefore there's some current that's actually leaving through. It's not as large as when the transistor's on, but it's still non-zero. And if you think about having billions of transistors, billion times something that's small can still be something that's quite large, right? Now, we had gate leakage, all right? And essentially what happens is does anyone want to guess that? What's gate leakage? And the truth is, it's important for us now. Maybe when Will and I started, it wasn't such a big deal because we were using quarter micron or half micron transistors and with thick oxides. Now we're at 7, or so therefore it's more of a problem. So therefore it's going to be a problem for you guys more than for us, or for me or my generation. So what is it? What's gate leakage? Okay. Remember, we're drawing. So this is oxide and the gate. All right. And remember, VGS. Do it this way. It doesn't matter, right? So essentially, what happens is this oxide, especially as you get to smaller and smaller devices, this oxide becomes thinner and thinner, right? At the moment, if I'm not mistaken, on a 28 nanometer process, it's 500 angstroms or something like that. It's only a few atoms, maybe 10 atoms thick, right? Only a few atoms. So therefore, what happens is it's not a big barrier, right? If you think about it, do you guys all remember your quantum mechanics? Who's done quantum mechanics? No? Oh, I mean, they used to teach it in second year in electrical engineering. So, okay, all right. So essentially what happens is, that an electron's not really a particle, it's a wave, right? And then also, if you've got a barrier, what happens is, usually in classical mechanics, what you say is you've got an electron. If an electron has less energy in the barrier, in classical physics, it gets just scattered back. It can't do anything. It can't climb it, right? In classical physics, right? Usually what you have to say is this electron has to have more energy than the barrier for it to actually be able to overcome the barrier. Classical. What happens in quantum is there's this concept of tunneling, right? And what happens essentially is that there is a finite probability that this electron can actually go through the barrier even though it doesn't have enough energy to go through the barrier, to go over the barrier. They can actually tunnel through. Right? And that's called quantum tunneling. And then what happens is, as you can imagine, as you make this barrier thinner and thinner, right? Therefore the energy, and if you're making the barrier thinner, which you're making this thinner, you're actually making this lower, right? So therefore the probability that it will tunnel through increases. So if we get more gate leakage. I'm surprised you haven't done any quantum mech.
And only a little bit, so didn't really go to understand all of them, just
So you know Schrodinger's equation and how to work out tunneling.
But just normally go through it and
Which course did you do that?
just in physics. It's just that there's another physics course at first year. But
Here or
Here.
First year physics, but it wasn't part of the engineering. It was part of your
it's part of
basic.
physics.
Okay. Oh, interesting. So there's no quantum. Okay, that's disappointing.
Maybe 1/3 of the semester spent on quantum mechanics of that physics. Yeah.
All right. Look, guys, what I would suggest, you're missing out. No, I'm being serious. You're missing out. What I would suggest over summer, I know you probably don't want to hear this, but get one of those books on quantum mech and just read it. Go through it. It's so interesting. It's so much of it. It's so different. It's so exciting. You'll learn something really, really useful, and especially if you're doing PhDs in nanoelectronics or anything like that, you'll be using it all the time, right? And for you, all of you, and that's why I was half joking when I was saying people of Will's or my vintage, we could use classical mechanics in order to do a lot of these problems and it didn't really matter. For you guys, especially as these devices become smaller, right, all of a sudden what happens is you need to start approximating as quantum mechanical devices. All the quantum effects start manifesting themselves and they start becoming important. For example, tunneling. You start seeing tunneling is important. You start seeing, scattering. You start seeing all this other stuff. You start seeing discretization in the energy levels through the transistor, right? And then also that affects the noise profiles of the transistor and the like. I would strongly recommend if you get a chance, just get a book, read through it. You'll be excited, because it's really, really interesting stuff. And it's going to be critically important for you guys, right? As I said, not that important for when I was learning, because we were using large devices, but for you guys it's going to be something that's really important. Anyway, I digress. Let's get back to this course, high-speed electronics. We'll talk about junction, the other thing is junction leakage, which is essentially there's leakage through there. And then I'll just put it down, but I won't go into something in its contention current in rush-shared circuits. And what we'll do is we'll discuss that towards the end of the course. As you can imagine, the dynamic power dissipation is the switching plus the short circuit power dissipation, and the static is just the current times the voltage for subthreshold leakage, gate leakage, junction leakage, and contention. Now, what I'll do a little bit, and then we'll start talking about activity factor and clock gating, is I also wanted to distinguish between power dissipation rather than dynamic and static. I also wanted to distinguish in some of the different ways that power is considered, right? And there I'm talking about you have in your device you have power, standby, and sleep modes, right? And active power is when you're actually using the device. Standby power is the device isn't necessarily doing stuff, but the clocks and this sometimes are going. Sometimes you can actually also gate the clocks, and we'll talk about that. You can actually, do a whole bunch of things. So, like, stopping the clocks, disabling certain types of ratioed circuits, and truly, if you're gating the clock, that's probably one of the most efficient ways in order to reduce power consumption or power dissipation in some of these circuits. Now in sleep mode, what you're doing is putting the device to sleep. Can someone tell me, what would you do? How do you, I'm saying you're putting the device to sleep, but you're not turning the device off. So what are some of the things? Well, we've talked about clock gating. What's one of the other things that you can do in order to put your device to sleep? Or part of the circuit to sleep?
Changing the register of the chip.
Yeah, but what's that doing? Yes. What's that doing?
Shutting down some additional clock, like
Ah.
PC, like
Okay, so it can be shutting down the clocks. What else can it be doing? Suppose you've got a whole bunch of, okay, you've got a whole bunch of circuits. Let me just say, as an example, if I draw this, this might actually help you. All right, so you've got VDD, and for argument's sake, you've got an inverter, and an inverter. Blah, 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 right? And we said that there's, power is being consumed because of leakage, right? Leakage or, sub-threshold. If you're not using this circuit, right, what's the other thing that you can do? What happens if I said to you, drop the supply? Right? And that's what happens. Right? What you would do, other than clock gating, the other technique that you would use is you would gate the supply. So therefore you drop the supply, so those parts of the circuit aren't actually getting any power, so therefore any power or any voltage, so they can't dissipate any power. They're not going to be, if you're putting something in deep sleep, and you're not going to use it, right? Just switch it off, right? And then what you're able to do is then switch it on when you need to. Now, it sounds easy in practice. There's some little complications there. You've got to make sure that you're switching on appropriately. You're saving states. You're bringing it up in the correct way. So there's a little bit of work that you need to do. But essentially, when you're putting your device to sleep, that's what it's doing, right? So they've had lots of engineers spend lots of time figuring out how to drop the supply and also to gate some clocks. Right? So they're the two of the most major components that people use, or techniques that people use, in order to reduce power consumption. Now, this is an example in the book where they've got a Sun processor. I don't know if you guys remember Sun systems or Sun servers. They used to be big in the 80s and 90s, and if you tried to do anything on Unix, anyone use Unix or Linux? Yes? No? The other thing you guys got to do is you've got to start learning how to use Linux. If you're doing any serious design, seriously, you have to be using Linux or Unix. Right? So, and it's free. You download it. It's an operating system. It's a little bit different. You've got to do it. Because otherwise, if you show up to a job interview and say, I've been using Windows, they'll laugh you out. No, I'm serious. If you're going saying, I'm doing chip design and I'm using Windows and I've never used Linux and I don't know how to script, they'll be like, okay, thank you very much. All right. Anyway, so, and Python. Anyway, so what I would, anyway, so this is just showing you the power consumption. But the point I was going to make was, leakage current, or the power due to leakage can be very high. We're talking about 21%, right? So it can be very, very high. All right, now let's go back to dynamic power consumption. And what we did is we defined activity factor, right? If you remember, I talked a little bit about activity factor, and it was, just for everyone's benefit, the activity factor is the probability that a circuit node transitions from 0 to 1. I apologise. And so here, again, just emphasising that if you reduce the activity factor, that's a very powerful way in reducing dynamic power consumption, right? and essentially in terms of dynamic power consumption, if you're not switching a device or changing the transition of the device, it's not consuming dynamic power, right? And essentially there all I'm saying is, hey, what's one way of doing this? And that is clock gating, which is, as your colleagues pointed out, you write to a register and it either switches down, the clocks or certain clocks in the processor, right? And it's a very common technique that people use these days. So therefore, if the processor is not really doing anything, or one of the cores on your processor isn't doing anything, usually what you do is you reduce the clock speed to it, so therefore it consumes a lot less power. It's not really doing anything, so you might as well think. But that has a disadvantage at it. It makes it, when it first starts up, it takes a little bit of time, right? Becomes a bit. Anyway, and essentially all that clock gating does is you put an enable latch. So all you're doing is you've got the clock and an AND gate with some enable logic, and what happens is the clock here is either the clock if the enable's 1 or it's 0 otherwise. Right? All right. Let's now talk about switching probabilities and activity factors. All right, now let's talk about switching probabilities or activity factors. And we said that activity factors, the probability, we're switching from a 0 to a 1. And just for everyone's notation, I know that you guys are all doing signal processing, so I know that you all love it a lot. So what I'm doing is I'm bringing some simple notation for you. So what I'm saying is the probability, I'm just defining Pi to be equal to the probability of node going from 0 to 1, and P bar is 1 minus that probability. Right, it's just a definition. And what we've got is we've got this table in order to work out the probabilities, the switching probabilities of certain gates. Now you can do this all by hand, right? And what I would suggest is, even though this table might exist, you may or may not get it. If I put it on an exam or a test, I may or may not give it to you, right? But come on, guys. I mean, if you had an AND gate, right, and we'll do the example here, and I said to you the probabilities are the same, there's only 4 combinations that you've got, right, to have an AND gate or an AND gate, right? It's either the first first input is 0 or 1, the second input is 0 or 1. There's 4 total number of outcomes. So therefore, the probability of going from a 0 to 1 is, come on. Anyway, so this is a table, these probabilities, but let's now look at a very simple example, and let's work out the switching probabilities. All right, so here what I've got is I've got a NAND gate, 2 inputs, and what I'm saying in this particular case is the probability of an A or a B is 50%. Right? I either assume that, or I'll tell you what. In most cases, assume the probability is 50% because that's what it usually is. Or if it's not, somebody will have to tell you it's some other probability. Right? Okay, so now let's look at the output for this node. I've got an ant on there. Okay. All right. Okay, so what are the inputs, A and B inputs? Well, they could be, let's say, A and B. The inputs for A can be 0, 1, B could be 0, 1, and then I've got all essentially the outputs here. So 0, 0, 0, 1, 1, 1, 0, 1, 1. And because it's a NAND gate, this is a 1, this is the probability, the output is 1 for the first 3 cases and 0 here. So the probability of going from a 0 to 1, what are the total number of outcomes that lead to 1? 3. Total number of outcomes, 4. So the probability of going from 0 to 1 is 3 on 4. Right? No big deal. You can do this by hand, right? What's the activity factor? Now the activity factor, I realise that I didn't define it anywhere. Okay. Now the activity factor, this is why you need to show up to lectures, right? Okay, the activity factor is pi bar. Right. So, if we've got the probability of going from a 0 to 1 transition is 3 on 4, what's the probability, what's pi bar? Quarter, right? Yeah, 1 minus 3/4 equals 1/4, right? So therefore, A, the activity factor is 3/16. All right, excellent. Now, you know, I've got this gate here, right? Who's willing to tell me what the probability, switching probability and the activity factor for this one is? All right, good. All right, you're awake. Perfect. All right, so the probability also is switching is 3/4 and the activity factor is 3/16. Excellent. All right. Now, let's now look at this gate here. Right now, I can, in the book, what they've got is they've put the inverter input here. I can move the two inverter inputs from here to this point here, right, if I wanted to. And essentially, if I do that, what I can actually do is, let's look at my inputs I've got, or if I leave it the same, let's say the inputs are, what we had is 3 1s and a 0. If we're inverting them, it's going to be 3 0s and a 1, and 3 0s and a 1. So let's now work out the probability of z equals 1, which is the probability of x equals 1 and the probability of y equals 1. Probability of x equals 1 is total number of outcomes is 4. Probability of 1 is, the 1 is 1/4. Probability of y being 1 is 1/4. So therefore the probability is 1/16, right? So you can actually work out your switching probability, and your PR switching here is going to be, for this circuit, right, because I'm taking into account that it's at this point in the circuit, right? Don't just think of it in isolation. Think of it as part of the circuit. So if my switching probability is 1/6, my activity factor is 1/6 times 15 on 16. Remember, activity factor is P times P bar, which is 15 on 256, which is what I had here. Right. Perfect, right? So now I can work out, for this particular example, I know my switching probabilities and my activity factor. So therefore, from this, if I'm working out my power consumption, right, I can say, well, if A and B changes at 50, you know, at a quarter, right, then I can now work out what my power consumption is going to be for this circuit, right, given a particular size and clock frequency. Now let's look at the following example. All right. Okay, and let me draw it out a little bit better. Or maybe I'm drawing it worse, actually. All right. And this is why during the exam they make you actually not draw it by hand. They actually force you to actually use software, and old people like me find it really difficult. Okay. Can I make a mistake? Yeah. Yes. Okay. Well, that's what it's supposed to sort of look like, right? All right. so let's work out the activity factors and probabilities, right? Okay, who wants to do this? You've got the values there. I've actually put them on slide number 9, but let's make this a little bit of a class exercise, so therefore we can actually, I can get some feedback and I can feel like I'm contributing something, right? And getting some feedback. Okay, who wants to help me with this NAND gate? Sorry? 3 on 4, right. But go through the process for me. Just explain it, so therefore I know that you know how to do it. So tell me. 4 outcomes, okay. So let's write the 4 outcomes. We've got 0, 0, 0, 1, 1, 0, 1, 1. Okay, so we're looking at, we'll say gate 1. Okay, and the outcome here is 1, 1, 1, 0. All right, so the probability is? Yeah, okay. Because that's the number of 1 outcomes, right? Yep, 3 on 4. And the activity factor? 3 on 16, okay. Okay, let's do the next one. Here. What do I do here? Okay, so I've got to look at the output from this one, right? So this is the thing I just want to make sure that you're looking at. I've got the output from here, and I'm inverting it before this is acting as a buffer, right? So therefore it's going to be, if I'm inverting this, so it'll go 0, 0, 0, 1, right? So what's the switching probability? Yeah? All right, and it's a quarter because I'm looking at the output here, right? Don't look at it in isolation. You've got to look at it from the input from the previous gate. Okay? All right, and the activity factor?
3 on 16.
Okay, 3 on 16. Okay. All right. Okay. How about here? This is where it starts getting a little bit interesting. So this is gate 2. Gate 2 and then let's look at gate 2. All right, let's gate 3. All right. What have we got? How do we? Yep. 8 outcomes. Yes, but why? Out of curiosity, you're right. So I'm not trying to confuse you. Yes, you're absolutely right. But why isn't there 4?
Be 1 and 0. One outcome from gate 2 can match. The C can give 2 inputs.
Yeah, because what I'm doing here is the probabilities, right? So there are 8 outcomes because here C's got 2 outcomes, 0 and 1, and here it's the probability is, if you're doing the table, you can do it 2 ways. You can actually do it, as we said, 8 outcomes, or you can actually say we can do 0, 1, 0, 0, 0, 1. Bloody hands. All right. And what we can do is we can say the probability of a 0, so we'll say this is C and this is D. You can do it 2 ways, right? One is, as your colleague has just pointed out, and we can say this is probability of half. And the probability of 0 is what? 3 on 4, 1 quarter, 3 quarters, 1 quarter. And this is a NAND, so this would be 1, 1, 1, 0, right? This is the output. So therefore, we have to count all the probability, all the ones that give us an outcome 1. So therefore it'll be 3 on 8 plus 1 on 8 plus 3 on 8 equals 7 on 8. Right? Did I get that right or did I stuff it up? No, good. All right. So here I've just used the probability of the data. You can do it that way, and that's probably easier. Or you can just do the combinations as your colleague has just pointed out. And the activity factor is going to be